Hello, so in today's video, we're going to look at the next topic in the A-level syllabus after proof by deduction, and that's proof by exhaustion. So yeah, in the last session, in the last video, we looked at proof by deduction, which is basically where we use algebraic arguments to prove a mathematical result. In proof by exhaustion, we want to prove a result by looking at all of the possible cases. So by going through case by case, all of the possible cases that we can have. And then by checking whether all the cases are satisfied, we can then prove the result because we know that all of the cases are satisfied. I think when we go through a couple of examples, it will become more clearer what I mean by that. So this first example here that we're going to go through. So prove that the cube of a number that ends in a digit less than 5 never ends in a digit less than two. Never ends in the digit 2. So yeah, in this case, in this example that we're going to do, to prove this statement here, we're going to have to cube numbers. Well, not every numbers, we'll see in a minute, but we're going to have to cube numbers that end in a digit less than 5. And then we've got to check all of the cases and check whether these cases end in a digit of 2. And if none of those numbers end in a digit of 2, then we've proved the result. And the same thing with this second example here that we're going to do. So prove that for all values of n, that could be 0, 1, 2, or 3. So basically, prove that when n is 0 or 1 or 2 or 3, we prove this result here that 2 to the power of n plus 2 is bigger than 3 to the power of n. So again, what we're going to have to do is we're going to have to substitute in n equals 0 into this thing here and check if it's true. Substitute n equals 1 into this thing here, check if it's true. Substitute n equals 2 into this thing here, check if it's true. And substitute 3 into this formula there, check if it's true. So this is proof by exhaustion. So we're going through each possible case and we're checking, is this statement true for all of our cases? So that's what proof by exhaustion means. So let's start with this first example here. So we want to prove that the cube of a number that ends in a digit less than 5. So for example, the number 943. So the last digit there obviously is a digit that is less than 5. So that would be an example, for example. So prove that the cube of a number that ends in a digit less than 5 never ends in 2. So we want to cube numbers that have a final digit less than 5, and we want to prove whether, we want to prove that they never end in a digit of 2. So let's go to the next page to look at the idea of this proof. So, this number here that I've written here, so 27,891. So yeah, this is a number that ends in the number 1. And the number 1 is indeed a digit less than the number 5. So this is an acceptable number that we can use. So if we cube a number like this, well, this cube number is going to end in 1. And we know that for a fact because 1 cubed, this digit there cubed, is literally 1. So we know that this number must end in the number 1. And we can use the same logic here. So when we've got this number here, this 999,999,94 cubed, we know that this number must end in the number 4. And that's because this last digit cubed is 4 cubed. And 4 cubed, we know, is 4 times 4 times 4, which is 64. And 64 ends in a 4 itself. So we know that when we cube any number that ends in a number 4, we're going to get a number which also ends in the number 4 as well. So that's the idea of our proof. So let's go ahead and actually prove example 1. So proof of example 1. So we're going to start off by looking at numbers that end in a digit of 1. So if we cube, sorry, let me write this neater. So if we cube any number that ends in a digit of 1, then we're going to get a number that ends in 1 itself. So then we get a result that ends in 1. And that's because 1 cubed is 1. I've actually forgot the first example that I should actually do, which is 0. So if we cube a number, because obviously 0 is a digit less than 5, so let's write this in next. So if we cube any number well, I should say really any positive integer. That's what I really should say here. So any positive integer. So any positive integer that ends in a digit of 0, then the result must end, so ends in 0 itself. And again, that's because 0 cubed is 0. So we can apply the same arguments for the next digit, so 2, 3, and 4. Let me just make the writing smaller on this page there. So again, the same process. So cubing a number, so cubing a number ending in 2 is going to give us a number ending in 8. And again, that's because 2 cubed equals 8. Then the next example, so cubing a number that ends in 3. So cubing a number ending in 3. So that's going to give us a number ending in 7 this time. So a number ending in 7. And that's obviously because if you cube 3, you get 27, and 27 ends in 7. So 3 cubed, sorry, I should write a cube there, 3 cubed equals 27, which ends in 27. So which ends in 7. And then the last example that we need, the last digit which is less than 5, is obviously the number 4. So cubing a number, so cubing a number ending in 4 is going to give us a number ending in 4 as well. And again, that's because when you do 4 cubed, you get 64, and that ends, which ends in 4 itself. Okay, so we've cubed, or well, we've not cubed every single number, every single positive integer, which has a final digit less than 5. We can't do that because we'd be here like forever. But what we can do is we can look at all the possible cases, and there are 5 cases. So there's a case where we have a number that ends in 0, a case where a number ends in 1, 2, 3, and 4. So they're the 5 cases. So we've looked through the 5 cases, and we've determined that we get numbers that end in 1, numbers that end in 0, numbers that end in 8, numbers that end in 7, and numbers that end in 4. So no number ends in a digit of 2. So let's just make a point of this here. So none of these results end in a digit of 2. So therefore, result is proven. So result proven. Because we get no cube number, which has a final digit less than 5 that ends in a digit of 2, and we prove that result there. So that's one example of proof by exhaustion. Let's look at this second example. So prove that when n equals 0 or 1 or 2 or 3, we get this result here. Okay, so we're going to go through again case by case. So proof of example 2. Proof of example 2. So the first case, so case number 1, is obviously when n equals 0. So if n is 0, then the left-hand side of our inequality, well, the statement that we're trying to prove, is 2 to the power of n plus 2. Let's write that here. So left-hand side is 2 to the power of n plus 2, which equals 2 to the power of 0 plus 2 in the case that n equals 0. And that's going to give us 2 to the power of 2, which is 4. And then our right-hand side in our statement, so right-hand side, was this here, so 3 to the power of n. So 3 to the power of n, but of course in this case n is 0, so 3 to the power of 0, that equals 1. So in this case we get that the left-hand side is indeed bigger than the right-hand side. So the statement is true in case number 1. I'll just put a tick by that just to just to denote that this statement is true in the first case. Okay, so now let's look at case number 2. So case number 2 is that n equals 1. Okay, so the left-hand side when n is 1 is going to be equal to 2 to the power of n plus 2. Well, that's just 2 to the power of 1 plus 2, which is 2 to the power of 3, and that's 8. So we get 8 there. Now the right-hand side when n is 1, so again, that's 3 to the power of n, which is just 3 to the power of 1. But 3 to the power of 1 is 3. Again, the number 8 is a bigger number than the number 3. So therefore, the left-hand side is again bigger than the right-hand side. And that's just what we wanted, because we want to prove that the left-hand side is bigger than the right-hand side in these cases. So we've got 2 more cases left. So case number 3, and that's when n equals 2. So the left-hand side when n is 2, again, that's going to be 2 to the power of n plus 2. But n is 2, so we get 2 to the power of 2 plus 2, which equals 2 to the power of 4. And that's going to be the number 16. And then the right-hand side, so that's going to be 3 to the power of n, but that's just 3 to the power of 2, which is 9. So again, the left-hand side is a bigger number than the right-hand side. And so we prove the result for that case there. And then we've got one more case to check. So case number 4, and that's when n is the number 3. So the left-hand side when n is 3, again, that's 2 to the power of n plus 2, but that's just equal to 2 to the power of 3 plus 2, which equals 2 to the power of 5, which is the same as 32. So that's 32 there. And then the right-hand side, let me just make the writing smaller or move the writing up. So our right-hand side in this case is 3 to the power of n, but n is 3, so we get 3 to the power of 3, which is 27. So still 32 is a bigger number than 27. So the left-hand side is bigger than the right-hand side in this case. So therefore, by exhaustion, we have proved that 2 to the power of n plus 2 is a bigger number than 3 to the power of n when n belongs to the set 0, 1, 2, and 3. So we just proved that result there because we looked at all of the cases and we showed that the left-hand side was bigger than the right-hand side. So that's another proof by exhaustion. So again, when we use this proof by exhaustion, the key thing is that we want to look at every case possible and we want to go through each case. And by evaluating each case that we have, we can then use that to build an argument that the result that we want to prove or disprove is true or not true. So yeah, that's the end of today's video.